Hi guys, Sajjad Hussain again with a new video. In this video I'm going to analyze Truss using SAP2000, not STAD, because I receive lot of requests from the students all over the world, I can say, that they want to see some videos on STAD instead of they want to see some videos on SAP instead of STAD. So I'm going to use SAP for the time being for some of the calculations and demonstration, and maybe afterwards I will switch to STAD or ETABS or some other software. So let me start with a very simple truss, as I started in STAD also. This is an example in Hibbeler's structure analysis 8th edition. It's a very simple truss, so I'm going to draw this truss in SAP and analyze it, and let's see, and we will compare the results. As you can see in this example, we know that the distance between A to B is 4 meter, B to C is 4 meter, and C to D is 4 meter. But in vertical direction only angles are given and the distances are not given. So we have to calculate the distance from AB to point G, that means this vertical distance, and of course this vertical distance, so that we can draw our grid lines along GE and along F, so that we can exactly locate these points. So to evaluate the distance from point G to line AB, we have to do some mathematics. So let's do some mathematics. We will use this figure. I copied this figure in OneNote, and now let us draw some lines so that it will be very clear. Now what we want to know, that this distance from point G be very straight. Similarly, we want to draw a line from here, and also we want to draw a line from point E. Now it's obvious that let this point be G dash, this point be F dash, and this point be E dash. Now we want to know the distance from point G to G dash, which is here. Similarly from point F to F dash. We know that the distance between A and G dash, this will be half of 4 meter, that means this will be 2 meters. So what we have to do, we have to draw grids at 2 meter interval in X direction, but in Z direction we have to evaluate this distance. That means we have to draw a grid line somewhere here and one grid line here. So we can say, if this is our grid line A, so this will be our grid line B, and this will be our grid line C. Similarly, this will be our grid line number 1, number 2, number 3, number 4, number 5, number 6, and number 7. So we have to draw 7 grid lines, 2 meter distance in X direction, and 3 grid lines in Z direction, A, B and C, but we do not know how far these are. So let's use our basic trigonometric skills. let's see. Okay, so if we consider triangle A, G and G dash, triangle A, G and G dash, we know that tangent of theta 30 degree, this will be equal to G dash divided by base, which is 2 meters. So that means this G dash will be equals to 2 times tangent of 30 degree. So let's evaluate. Tangent of 30 is 1 upon under root 2 multiplied by 2. So this comes out to be 1.154.7. So this value G to G dash comes out to be 1.1547 meter. Similarly, for triangle F, A and F dash, the bigger one, we can say same tangent of 30 degree. This will be equals to F dash over AF dash. This is 6 meters. So here comes out to be F dash will be equals to 6 times tangent of 30 degree. So F dash will be equal to 30 tangent multiplied by 6, 3.4641. So this comes out to be 3.4641 meter. So now we have to draw grids at 1.1547 and 3.4641 in y direction. So let us start our model in SAP. So file, new model. We know that the values of forces are in kilonewton and distance in meter, so we have to select the unit first, kilonewton meter C. Material, okay, United States, grids only. Now in X direction there will be 7 grids. In Y direction there will be only 1 grid. In Z, that is the upward direction, there will be 3 grids. Grid spacing in X direction will be 2 meters. Grid spacing in Y, nothing. Okay, let it be 0. There is only 1. And here in Y direction they are different. So for the time being, let's put 1. Okay. Now we don't want this 3D view. Now let us edit the grid. In Y direction is okay, but in Z direction we know the first is 1.1547 and the second was 3.4641, I think. Let's have a look once more. 4641, 4641 and 1.1547. 1547, yes. So these were the values. Okay. So something wrong. This was 3.4641, so it was 3.4641. Okay, something wrong. All right. Three 3.4641. Okay. Yeah. So now we have to develop our model. Let's see. So first member will be A to B, which will be 4 meter long. Let us define material. It will be a steel. So let's add. We know that it is a massless steel, or we are not considering the dead weight, so we are taking the mass equal or the density equal to 0. And let us define this material as a truss material. Okay. Let us define the section properties. Frame. Well, normally we can take this value and we can add section properties from here. Let's say we select an angle of 3.5. Okay, right. section property frame here. Okay, by default we took truss, no problem, that's good. So we have to define our members. First we have to define A to B, which is 4 meter long, from A to B, which is 4 meter long, then from B to C, which is another 4 meter long, then C to D, which is 4 meter long, then D to E, then E to F, then F to G, and G to E again. Skip. Now again we have to join from B to G, from B to G, then from B to F, F to C, and from C to E. So here is the complete model. Now we have to assign, let's close this one, full screen, that will be easy. Now let us assign restraint conditions. We know that point A is a pin joint connection, so we are applying over here a pin joint, and a roller support here, apply. Okay, so we have applied the supports also. Now let's apply the forces. Here it was 3 kilonewton, 3 kilonewton, and here it was 2 kilonewton. Let's see load pattern. We have only one load pattern over here, we don't need anything else, so this is fine with me. Define load cases. We have dead load and model. We are not doing any model analysis for the time being. Let us delete this load case, and then we are not going to have any definition of load combination or anything else, so let it be like this. Let us assign the loads, forces in global z direction. First is -3, it is assigned at this point, sorry, and this point also. And there is a 2 kilonewton force which is applied here at the top. So we have already defined these forces. We can put the grid off now, that's no more needed. Okay, so grids are gone. Let's save this model. Let it be Truss 1. Now we can analyze, but before analyzing this, we have to select what type of analysis we are looking for. It is not a space frame, it's a plane frame, so we have to select plane frame. Okay, and then we have to analyze, run analysis, only one load case, yes. This is the deformed shape. We are not interested for the time being in the deformed shapes. Let us display the forces. We want to see axial forces. We want to see the values. Okay, so here are the values. Let us check. Sorry, I closed that one. Let us pull that example. Here it is. So now we can see that force in AG is equals to 8 kilonewton. This here we got 7.98 kilonewton, fair enough. Force in AB is 6.928. Force in AB is 6.9, correct. So that means what we are getting over here is very exact result whatever is given in the analysis. So this is the way Truss is designed in SAP 2000. We can get all the internal forces, support reactions, everything. So hopefully you will like this video, and in future I am going to present some more videos of truss analysis with SAP. Hopefully you will like it. Thank you very much. Bye.